So he's a very versatile and a brilliant mathematician with varied interests. He has worked on many problems in low-dimensional topology, in geometry, in Riemannian geometry, metric geometry, hyperbolic geometry, symplectic geometry, and all that. He's also worked on many problems in probability theory on the interface of mathematics and biology. Recently, he has been exploring automated theorem proving, and this talk is in that theme. The title of his talk is the question Automating Mathematics. So, welcome, Professor Gadgil, and over to you.
Oh, thank you very much. Thanks, Pranav and Kesom, for the kind invitation and the kind introduction. Yeah, so this talk is a little bit incongruous in this conference, which is mostly mathematics. This is weakly related to mathematics. And as Pranav pointed out, this is a question. So the question mark is the important point in this title. Okay. But of course, I don't want to speculate. What I want to talk about is things that are true and in one way or the other related to the theme of this talk. Yeah, so it's automating mathematics. So what is the question? So really, I want to formulate it as a somewhat precise question, and which is, can computers acquire all the major capabilities used by us, people in mathematics, either as individual mathematics or mathematicians or the community, in discovering and proving mathematical results. So discovering concepts as well and proving mathematical results. Yeah, so computers can do many things. Can they do everything? That is everything important. And when I say at roughly human levels or comparable to human levels, of course, when you say can they acquire on what time scale, do you mean years, decades, centuries? And the important point is how. I mean, they're not going to do it by themselves. They're not another species or anything. It's people who have to do it. And that is really the question of interest. I mean, how can you do it? Is it possible? Mm. So computers are already used in several ways in mathematics. I'll talk about that a little bit, and perhaps that may be a more useful portion. Many of you might already be experts in Sage or using MATLAB or Mathematica for various things. You would have heard Manjunath's talks where he showed all these plots to get your histograms for guessing Wigner's semicircle law, whatever else you want to do, or that some distribution is bimodal. But they're used in a way in mostly in limited fashion, but in other cognitive domains, they are used in a much more general way, more or less as much as people, uh, they can do whatever people can do and more. Yeah, and so this suggests they can do much more. And so that I'll be talking about two things really. One is computer proofs at present, and for computer proofs in the future, obviously I can't talk about the future, but I'll talk about the present in other domains, and that will give you a hint of how the future would be. So I should also mention here that automated theorem proving is closely related in more than one way to a subject which is computer verification of proofs. And I'll talk about computer verification and how it's related to automated theorem proving, but roughly many mathematical proofs in the literature are just wrong, including papers in the annals of mathematics, etc. There is a fraction of them which are, a certain number of them which are just simply wrong proofs. And to avoid this happening, and since mathematical literature depends on other parts of mathematical literature, this can be a serious problem. So to avoid this happening, we have would like to have computer verification to make sure that everything in the literature is correct. So this is closely related topic. Okay, so I'll be talking about these related themes here. But first, what about computer proofs actually in mathematics? Let's first dispose of what we would have liked to have. So Hilbert actually formulated this. What we would like to have is a universal deducer. You write a program which you give it a statement, it either proves it's true or it proves it's false. Okay, but we know due to work of Church and Gödel and Turing and so on that this is impossible. You cannot have a program which takes this as an input. This incidentally has a practical consequence. It tells you that there is no, given two proving systems, you cannot have one being, I mean, you, of course, one particular one may be bad, so another may be better than it, but there is no best deducer, because any proving system is going to fail to prove some results due to these results of Gödel and Turing and Chaitin and so on. But on the other hand, any given proof, if there is a proof, can be found by some deducer. Just one dumb one which looks up only that proof, for example. Okay, so you cannot have a best deducer. But this may be relevant as you go around designing them. So as I said earlier, like I should emphasize, the goal of all this is to try to understand how we can do things. They're not going to happen by themselves. Okay, but you can't have a universal deducer, that is clear. But nevertheless, computers have been used for many things. The most famous original one is the four color problem. So any map can be colored with at most four colors. Apple and Haken showed this in 80s, early 1980s. At that time, computers were much more primitive. So there were many issues at that time which are no longer issues with this kind of proof. Okay. More recently, around the turn of the century, that is 20th, around 2000, year 2000, Kepler conjecture was solved by Hales. And he showed that is what the figure was at the beginning of this section. So this is Johannes Kepler of Kepler's laws of motion had conjectured the most efficient way to pack spheres is hexagonal close packing, or equivalently the cubical close packing. There's a transformation that relates the two. And these two are hence the same density, that these are the best. It was proved as recently as I said, 20 years ago. Even though it dates back from, I don't know, 1600s, 1700s. More recent one is an interesting example. I'm just picking these out. A Boolean Pythagorean triples problem. This is from maybe a year ago. So this is a Ramsey theory kind of question for those who work on these things. But it's not purely graph theoretic. It has to do with numbers and graphs. Okay, so if you want to color the positive integers with two colors, either red or blue, so that if three integers satisfy a squared plus b squared is c squared, like 3, 4, and 5, they're a Pythagorean triple, they can't all be the same color. So 3, 4, and 5 can't all be red or all be black. So you color red and black. So the question is, can you always do this? It was shown that no, you can't. A compactness argument will tell you that it's equivalent to ask whether for an arbitrarily long integers from 1 to n, for all n, you can find such a coloring. And there is a certain number, 8,000 something, up to which you can find it and beyond which you can't. And finally, another example I'm picking out for a couple of reasons, Smale conjecture for hyperbolic three manifolds. So Smale conjecture, the original one was about spheres, proved by Alan Hatcher in 1980 or so. So the general statement asks whether for a given space, the diffeomorphism group, deformation retracts onto the isometry group. If you don't know these terms, you can ignore it. This is an example of something. So in fact, Gabay, Meyerhoff, and Thurston proved homotopy hyperbolic manifolds are hyperbolic. This is using the same computer proofs that proved that. Using it, so there was a series of papers of Gabay, and then Gabay, Meyerhoff, and Nathaniel Thurston have a paper where they proved using a computer-assisted proof that you have a certain technical condition called insulator condition satisfied by all hyperbolic three manifolds. You don't, as I said, if you don't know details of these, you can just ignore it. The homotopy hyperbolic is subsumed by Perelman's work. So Perelman, but the Smale conjecture, as far as I know, there is no Ricci-Flew proof yet. Now they may be. Perelman certainly didn't prove it using Ricci-Flew. So this was proved by Gabay some 3-4 years after that. So these are examples of proofs. Well, how do you prove them? Well, computers are used, of course, for computation and enumeration. These are two sort of dumb ways you can use computers, as everyone knows. Many people, most of you would be familiar with some amount of symbolic or computational algebra. Symbolic algebra is maybe integrating, differentiating functions and many other things, and things like GAP and SAGE are used for computational algebra quite a lot for groups, representations, various things. Now, compact enumeration I want to emphasize because I feel this is underused. Whatever mathematics you're doing, there's a chance you don't quite realize that you can do this. So enumeration means you have a finite set and you want to prove, for example, a function is positive there. You just check at every point. But compact enumeration is little different, and this was used, for example, in the Smale conjecture, also double bubble problem, which is you have a continuous function and perhaps you have bounds on its derivative, and you want to prove that it is positive on a not a compact set, but on a compact set, not a finite set. Well, the trick is that at any point, if you calculate the value and show that it is positive, then because of bounds on the derivative, you can show it's positive in a neighborhood of that. And so using this, you can cover the set, and by compactness, any open cover has a finite subcover. So if the function happens to be positive on a set, with enough calculation, you'll be able to find it. Closely related to this is exact real number arithmetic. So this is where, well, real numbers can't be exactly represented, but there are various ways around this. For example, rational numbers can be exactly represented by specifying numerator and denominator. And when you have such a rational number, so real number, you can find an interval which contains it with rational endpoints and do interval arithmetic. There are a couple of other ways in which you can implement exact real number arithmetic. Okay, linear programming is extensively used. In fact, Hale's result was a combination, that Kepler conjecture was a combination of linear programming and enumeration. Namely, to prove Kepler conjecture, what Hales had to do was solve an enormous number, million linear programming problems. Linear programming can be exactly solved, so can enumeration. So between that, you get the proof. Okay. The other thing is semi-algebraic geometry, as people don't often know. Tarski already showed is decidable. This means that if you have equations over real numbers, okay, which are given by equations and inequations, and you want to know whether there is a common solution for all of these. Many problems like unknotting can be actually formulated in this sense. And using Tarski's original algorithm is not efficient, since then have been improved. Using one of these algorithms for real semi-algebraic geometry, they're doubly exponential. You could solve many of these questions. Okay. For example, Prathamesh and a couple of authors, Prathamesh is a former student, have a paper doing this for knotting, for deciding whether something is knotted, a knot is unknotted or not. Okay. And then there are what are called SAT solvers and SMT solvers. These were used for Boolean, Pythagorean triples problems. So the idea is, most of you would have heard about P versus NP. And the result that established that was that a lot of problems were equivalent to one particular problem, which is SAT, and or if you wish, a specific case of this called 3-SAT. So we think all of these do not have polynomial algorithms, but the line between polynomial and exponential in practice is somewhat arbitrary. There is another way you could use this Cook's theorem, which tells you all these problems are equivalent to SAT. Namely, focus all your efforts on finding heuristic ways to solve SAT better. Then you can solve all other problems if you can map them to SAT. And SAT solvers exactly do this. SMT solvers are a little more general. So the idea is that you spend a lot of effort and find various tricks and heuristics to better and better solve these specific problems and map lots of things to these. Okay, so these are ways in which computers are used quite widely. But I'd like to say, for a working mathematician, perhaps the main lesson is they're not used as much as they can be. You can probably use them in your field more than they're used at present. Here's a case of a different kind of proof. This was what is called Robin's conjecture. So this was a conjectural characterization of Boolean algebras. Boolean algebra is the algebraic structure corresponding to true or false. So you have two operations, or and, plus the operation not, two binary operations, or and. And because of distributivity, you can get rid of and, write it in terms of or and not. So you can think of just two operations, and or and not. And then Robin's conjecture. So basically there was Huntington showed that if you assume that you have or, which is commutative and associative, and an equation is satisfied, not is an idempotent, so not A is A, and you have one equation satisfied called Huntington equation for not and or, then you get a Boolean algebra. You get all the properties of a Boolean algebra. And Robbins conjectured that instead of Huntington's equation, you can have a simpler one, which is Robbins equation. So this was conjectured in the 1930s, and many people worked on it, including students of Tarski and so on. So it was a serious effort that went into it. But finally, it was proved by an automating theorem proving system, EQP. So this looks like a big breakthrough. In a sense, it was. Unfortunately, if I search today, this seems to be so far isolated. There is no other case that I see in the literature where a fully autonomous deductive theorem prover proved problem. By the way, if you have any questions, please ask if you're on Zoom or ask in the chat, and one of the moderators can feel free to interrupt me because many of these things may be somewhat unfamiliar. So what do you have if not fully autonomous theorem provers? You have what are called interactive theorem provers. Okay, so interactive theorem provers, they're software systems where proofs are obtained by human machine collaboration. And the computer has two roles. It helps you find the proof and it checks correctness. Okay. And the ease of proving in such systems depends on two things. Firstly, what the proof is in this system. Okay, which is you want the proof as the computer notes it to be quite concise, not extremely long, and also composable. That is, the pieces of the proof should fit together like Lego blocks, as they do in the way we think of mathematics, but not in official foundations. And also, the elaborator is something where you give part of the proof, I mean, a sketch of the proof, it finds details, fills in details. Tactics are things which help you find proofs. So it depends on the strength of its elaborator on the proofs. Okay, and the former depends on what foundations you use. This is a topic in itself, which I won't go into because of time limitations. And the latter is essentially automated theorem proving. So the first part depends on foundations, which is having nice proofs. There have been major advances in these over the years. It's very interesting stuff. As I said, I won't go into it. And so interactive theorem provers depend strongly on automation, because if you have to supply a fully detailed proof, it is too much work. So you depend on the system being able to help you with filling in more and more details. And at an extreme, you can say everything is a detail. You write a theorem and the proof says solve this and it solves it. That becomes fully automated. Today, we are somewhere in between the two. But if you have good foundations in a system like ACDA, if you play around with it, actually supplying all details is fairly pleasant for relatively small proofs. So both these things play together. Okay, so here's a conceptual issue here. Who guards the guards? So you say computer verified the proof, but how do you know the program that verifies the proof is correct? So why should we trust that anymore? So this was addressed by De Bruijn in 1968. He made the first computer proof system called Automath. Already he had this principle there, which is that you have a small trusted kernel in less than 1,000 lines of code, say. Okay, so this would be small. And in the modern world, you should say it should also be open sourced and well documented. And you check the trusted kernel. And the trusted kernel checks the rest of the system, meaning checks the proofs output by the rest of the system. Okay. And so if the trusted kernel is correct, which can be independently verified by many people, then your whole proof is correct. Okay. A very good implementation of this is the lean theorem prover. It has at least three that I know of, proof checkers, and they're written in three programming languages. C++, in which lean itself is, Haskell, and Scala. And these languages are different enough that the temptation to copy paste is small, because if you copy paste, you may copy paste something that is wrong and propagate errors. So these really have been independently written, independently checked, and they all work. So any proof can be checked by these separate systems. So this will mean how you solve things. So this solves. So this is why computer verification of proofs actually gives you certainty, even though somebody has to check in principle, but you don't have to check the specific proof. You only have to check the kernel. Okay. So for modern times, here is a New Yorker cartoon, which is the analog of that. It says, "Who sanitizes the sanitizer?" here, like who guards the guards. Okay, so here is something that has been done with the interactive theorem provers. So Fate-Thompson theorem has been formalized in the system called COC. by George Gontier and with collaborators. He was the leader of this. Fate-Thompson theorem, sorry, I should say what this is. This says that all odd order groups are solvable. So in the classification of finite simple groups, you can think of classification of finite simple groups as Everest that you want to climb collectively as mankind. Maybe Fate Thompson is the highest hill which is short of climbing Everest. So it's one of the big landmarks along the way to this. It is a 300-page paper in Pacific Journal of Mathematics. Until then, all the proofs in that field were 7-8 pages. So this was suddenly a much larger proof, which surprised everybody. Formalizing this also involves formalizing all the relevant algebra as well. Now, Lean Mathematical Library has formalizations of lots of undergraduate mathematics and perfectoids and various advanced results as well. And there is a very active effort led by Kevin Buzzard, and then on the other hand by uh, well, I should not forget names, but I'm forgetting people at Carnegie Mellon University, Jeremy Avigard, and so on. So there's nice collaboration between people who are writing the lean prover, who are in Microsoft, and people who are in universities who are building this library. And this value of the library is more than one. One, it tells you that you can formalize mathematics in practice. It also helps you formalize both because you learn how to do it by doing it. Also, when you're formalizing your theorem, you can use undergraduate mathematics, for instance, that you do. But it also gives you data for machine learning and also advanced searches. You see, when you search things in mathematics, say MathSciNet, you're searching by text, but really you want to search by the meaning of the result. That is what you would call semantic searches. Okay, so this is what I talk about interactive theorem provers. Now I'll go on to another topic, which is a digression. It's not directly relevant to what I do, but I think it's quite, if you're in the business of doing mathematics, you might find this kind of reassuring about the value of mathematics and interesting as well. So this is what are called formal methods. So what are formal methods? Formal methods is where we specify software, hardware. It could be a communication protocol. It could be a cryptographic system, something in precise mathematical terms. And then you give mathematical proofs of correct behavior. And these are computer verified mathematical proofs. Okay. So this is done in engineering applications. This gives, of course, much greater degree of correctness. So there is still one point of failure, namely when you abstract something, when you mathematically model the real world, you may make a mistake there. Like De Bruijn principle, there is some little bit which you have to human check is correct. But once that mathematical modeling is correct, everything else is computer verifiable. Okay, this leads to a much greater degree of correctness. There are interesting stories, in fact, not that long ago, where a very widely used sorting algorithm, including the ones used in a lot in your Android system and so on. Some people tried to computer verify this as a European group, and they found it very difficult. And then they realized it's because it's wrong. So things that are widely used are actually wrong. So computer verification helps. But if this is so good, why don't you use it? It's because proving is hard. So it's much harder than writing the code and putting tests. So you have to make a trade-off. And so the point is that they use interactive theorem provers. And if we can prove better, then we'll more often try to prove things instead of just testing them with simulations or other tests. Okay, so the role of mathematics will expand if you can do computer assistance and become better at using mathematics. Okay, but as I said, today it's really hard to use proofs. So you do it only when you need to be completely correct always. If you can be occasionally wrong, or if you can be slightly wrong, then you don't bother. Okay, if you're writing a web server like a department web page, you don't care if occasionally a user gets something wrong. I mean, misformatted or anything like that, because it's not worth the effort of proving correctness for that. Okay, so what are such cases? The first one is example is Intel's chips. So in 96 or so, you had a floating point error, which was found in Intel chips. The cause of the error was silly. Someone had made a mistake in a lookup table, but nevertheless, an error was found actually by a mathematician experimenting with prime numbers, not any industrial application. But for Intel, it turned out to be very expensive because after a lot of back and forth, they had to offer to recall the entire line of chips. Also, when you're fabricating things, you make one mold or master copy, and that has to be changed. So in many industrial processes, you make a master is more expensive, and then making copies is easier. Now, softwares can just be patched, but hardware you can't. You have to remake your mold, and then you have to physically bring back things and replace them. So it can be very expensive. So it's worth really trying harder to avoid the error. The second is the obvious reason, which is that there are things which are safety critical. This Therac 25 radiation machine was one which had a problem more with its user interface, one would say, rather than software. But nevertheless, people being given radiation for treatment for cancer got an extremely big dose of radiation. They died as a result. So in medical and transport, various safety critical applications, you simply say that it's not acceptable to make errors, because lives are at stake. The third is something which is actually very important, and which is why system software people are most involved in these, which is not so obvious maybe, which is, so again, here is an example. The WhatsApp Pegasus attack was in Indian newspapers quite a lot. So Pegasus, an Israeli company, managed to hack WhatsApp. And it did it because there was an error at the server end in WhatsApp, which caused a buffer overflow. The point is that that error was triggered by an extremely rare condition. So probably over decades, it would never be triggered, except that a hacker or other malicious person will deliberately search for errors. Okay. That is, sorry, I got a beep. Was that a chat message? Okay, I assume it's something unrelated. Yeah. So the thing is that when you have a WhatsApp, yeah. So when you have a bug in system level thing or a server level thing, and someone wants to hack you, they will target that and find a way to compromise your system. So even if in the natural course of things, it would never be target, you would never encounter it. It's a vulnerability which can be deliberately encountered. So even if it's a set of measure almost zero, you will still find things hitting that. Okay, so it's not random in that case. And indeed, here are examples of people who do use formal methods. Intel, as which is Core i9, this is the latest chips. They have been increasingly using formal methods at more and more levels to avoid the kind of floating point errors that you have. A second example is safety critical. The driverless metro in Paris uses safety critical equipment. This is an example I like because the Alstom, the same company's group in Bangalore, is also getting into using formal methods. We had some interaction with them because they needed to learn some mathematical foundations. But so Indian trains also perhaps in the future, maybe on either our metros or the dedicated freight corridor might have formal methods used to check this. And Scala is the language I most use. That's why I'm aware with it. The next version of Scala, which is getting released over the next 2-3 months, so it's not in the distant future, has actually been formally verified by Koch. So the compiler has been formally verified. This is effectively system level software. Many things run on Scala, including, for example, Netflix. Things that you're all aware of are running on that. So they don't want it to be hacked. And so they have actually verified, and some popular language features were even removed because they said they're inconsistent. You may like it, but we won't leave it there if it's inconsistent. Okay, in the next version. Okay, so now I'm going to digress. So far I've talked about computers proofs, but computer proofs, they are interactive proofs are getting higher and higher. Fully autonomous proofs are not are going up with them, but they're limited. So we want to move to other domains where computers can do a lot more to try to understand what they can do and how they can do it. Okay, so I'll turn to games and then I'll turn to other applications slowly over time. Okay, so the top is the title for the first major paper on uh, chess. Programming a computer for playing chess was the title of a paper by Claude Shannon, the founder of information theory. So the first paper on this was Claude Shannon, first program for playing chess, which had to be executed by hand, was written by Alan Turing. I'm saying this to point out that this was considered clearly a very important paper. The two giants of communication, information, and computing of modern times were involved in addressing this question. So, how do you get a computer to play chess? Well, I'm sure most of you have played chess. I'm not a good chess player myself. Some of you will be actually very good chess players, but I know enough to say these things. Hopefully, you all know enough to understand. So, you need two things to play chess. One is when you see a board's position, you have to know how strong white is or black is. And a simple way of knowing this is you know the value of each piece. You know a queen is valuable and more than a pawn and a bishop, and there are usually numbers that you associate to it. And in Shannon's first paper, he used these standard numbers, simply the number of points for a queen, bishop, knight, pawn, and rook. And then he said that if a pawn is doubled, we'll give it half a point. That's all. He will stop at that. Okay, this can be refined more and more. But also, what moves should you consider? You may consider all moves. That will take a lot of time, but you may only consider certain moves, and you want to decide based on that. Okay. And so, how do we play chess? So, Shannon's paper, he did not consider a policy. He considered only the value. His policy was try everything. But what you do is you consider the value at the end of a sequence of moves. And you use a minimax procedure. Namely, let's assume we are looking only two moves ahead. So I consider all my moves and I consider all my opponent's moves. And the score of any given move of mine is the lowest score after all my opponent's moves. Okay, so it's minimum score after all my opponent's moves, and I'm maximizing my score. So you alternate minimizing and maximizing. And so if you want to look four moves ahead, again, you do the same thing. You look any number of pair moves ahead, alternatively minimize and maximize. Okay. And this can be refined with various moves. So I'm just mentioning two heuristics, which were among the first ones and most important ones that were developed beyond Shannon. One is quiescent search. In fact, this Shannon himself had mentioned this. So it can be very misleading. In chess, very often you have piece exchanges. So if you look six moves ahead, and the sixth move is somebody taking my opponent taking my knight, and my next move is my taking his knight back, and these two are canceling. So if I look six moves ahead, it looks like I'm in a terrible situation. Actually, I'm in the middle of an exchange. So quiescent search means you stop checking at a point when things are quiet. If the next move is going to be a killing of a piece or queening of a pawn, don't stop at that stage. Look that much ahead. Don't just go a fixed number of spaces. Go till fixed number of steps, but only if things are quiet. And alpha beta pruning is again, okay, let me take an example. This is just an example of a heuristic, but it's relevant as far as policies are concerned. Suppose we are looking only, say, two moves ahead. Okay. And I try a good move and I look at all my opponent's response. And I know a certain score at the end of it is 10. And then I try another move. I mean, try meaning mentally try another move. And I see a opponent's response, which shows that the maximum already at the end of that response, my score is 8. Then I don't have to consider all the other responses. I prune. So if you have several steps, you actually have an upper bound and lower bound for what your score can be, and you prune based on that. Okay, so these are examples. So the relevance of this to the above is, as I said in Shannon's paper, the policy was just try everything. But if as far as alpha beta pruning are concerned, even if you are trying a fixed number of moves, the order matters. So having a good policy is important, what you consider. Okay, so chess openings give a policy. And endgame tables, which are used by computers, also give a policy. Okay, so Bob Pike, who's one who created Unix operating system, for those familiar with such things, Linux and hence Android are based on that, so is well known. Went around in 1980 or so to various chess events where you would have tables of all possible endgames. You go around with a computer which had these tables. You can simply backward calculate. So these give you extreme policies. Openings means in the early stages, you don't consider all legal moves. You consider only a fixed number, most of which have names, some opening, another opening, variations, and so on. Okay, so maybe I've said more than I need to about this, but let me point out here. Now back to modern times. So in 1997, Deep Blue computer built by IBM defeated world champion Gary Kasparov. This was a little bit controversial. There were many issues here, but according to Kasparov, 96 to 2006 was the time when the best chess players and the best human chess players and best computer chess players were roughly competitive. Says after 2006, computers have gone far ahead of humans. Now, cell phone programs easily beat the best chess players. Okay. So how were these designed? They were based on extending the above methods to elaborate values. That is, instead of just saying, so as I said, if a doubled pawn is counted as half, but a passed pawn, you give extra values. And then between two versions of Deep Blue, some chess players realize there are some things called semi-passed pawns. I don't even know what they are, but you give them extra credit, etc., etc. But nevertheless, Deep Blue was very limited in certain ways. It was very good in certain ways and very limited in certain ways. Okay. So in particular, the value and policy of Kasparov were much better. So Kasparov could look at a board, or any really good chess player could look at a board and say whether white or black is stronger, far better than Deep Blue could. Could also look at the board and say what moves to consider, far better. But Deep Blue compensated by considering far more sequences. Okay, so this, I'm emphasizing this because, as I said, goal in automated theorem proving, at least as I would formulate it, is that you should have all the capabilities. Not that a computer is good in some ways, bad in some ways, and tries to compensate. The other is also important. You do want to get computers to be better and better in the ways where they're already good. But I would rather like to say that in automated theorem proving, we should focus on where they're hopeless and see how that can be lifted up. Okay, so in particular, Deep Blue was hopeless in some ways, but made up by being extra good in these ways. And so you changed to a different challenge. Okay, so Chinese game called Go, the number of legal moves is much larger. So if you want to try everything, it becomes really painful. You can only look 2-3 moves ahead. But even more importantly, because it's a very symmetric kind of game, you even Go masters cannot describe why one player is stronger than the other. Okay, so what we use is effectively what is called tacit knowledge, knowledge that cannot be codified. Okay, so the best example of tacit knowledge to me is riding a bicycle. When you learn to ride a bicycle, it's not that you're told how to move each hand and how to balance your weight. You learn it, but the other person also has to learn it. Swimming is the same. Okay, so a lot of things we do in life are tacit knowledge. And so in Go, strength, even in chess, tacit knowledge was important, but in Go it was almost all tacit knowledge. So it makes it much harder than chess for computers. Nevertheless, in 2016, the Go playing program AlphaGo defeated the 18-time world champion Lee Sedol. At that time, Lee Sedol, while he was widely considered a legendary modern chess player, was rated number 3. Number 1 was a young Chinese genius named KG. It took a few more months for AlphaGo to get better, but when it played it him in January, so Lee Sedol was defeated 4-1, and in KG was defeated 5-0. So the stronger player was defeated comprehensively. That was a clear victory. So what happened? What changed? The change is the policy and value functions of AlphaGo were deep neural networks that were trained. A human did not try to write rules. This is the lesson for mathematics also. We don't try to codify what we know how to do. Okay, we simply assume that things are trained. We simply figure out how to train things. How do you do it? Initially, policy network was trained by learning to predict the next move from games of expert players. So there's a big bank on the internet of games, Go games, like there are for many other things. And what you do is you try to predict what is the next move an expert will make in the given situation. Note the number of games is so huge that you would not have seen that exact game. You have to somehow pick up the properties of the situation from which you predict this. Okay. Yeah, so it's much more complicated than regression or just choosing things, but I'll come to that. So these deep neural networks try to predict the next move of an expert, these things, player. And the value network, seeing how strong a position was simply that you play the game to the end and see how often white wins and how often black wins. Okay. You play from a given board position to the end again and again and again. Again, you only can sample a small fraction of board positions, but based on this, you do it. And even when it comes to policy, you have to do self-play. Once you have initially trained it this way, you keep playing against yourself and then learn what is a better move. Okay. So we know that AlphaGo, even though the hardware had advanced a lot, considered far fewer sequences of moves than Deep Blue. So instead, most of its time was spent deciding what moves to consider and evaluating value. So it's become more human like in that way. Also, AlphaGo showed some great originality in one particularly famous move. By AlphaGo's calculation, the probability was only 1 in 10,000 an expert would have made it. But AlphaGo calculated it was a good move, and Lee Sedol was so surprised that he got up and walked away and had to pace around for 15 minutes before he could compose himself to get back to play, because it was utterly something he had never seen, even though he was the 18-time world champion. So you get originality by self-play. Okay. So what is this? So a little bit of a mathematical digression for those who have not seen deep learning. If you know machine learning, you probably know more than this. But so what is it mathematically that's going on in all these machine learnings? Well, you're searching. Let me stick to finding the policy, predicting what a expert player will do. For concreteness, we'll stick to one problem. What we want to do is search for an optimal policy, that is optimal predictive policy, in a space of functions. You want to find the best function in a space of functions where you choose an appropriate loss, which is how often you're wrong in predicting or how often you correctly predict. Okay. So far, so good. This is what you do in linear regression also, right? Everyone would have seen linear regression. You find that M and C so that the line fits very well. Okay. But in linear regression, you're finding a couple of numbers, or in multi-dimensions, a matrix or something. You're finding a bunch of numbers for which parameterize a linear model. Here, instead, we're looking at a different class of functions. And this class of functions are all compositions. Ck composed with Ck minus 1 composed with C1. Each of these I'll call layers. So far I have not said much. I've only said the class of functions we look at are compositions of other classes of functions. So number of parameters are of course the number of parameters of this plus number here plus number here. Okay, so what are these layers? A typical layer is of the following form. Okay, it's a function of the form. I look at ax plus b, a linear function, add to that a constant, so it's an affine function, and then compose it with a sigma, where sigma, which is called the activation function for whatever analogy with the brain, is a typical example of sigma. It need not be exactly this. Is what's called a sigmoid function, e to the x by 1 plus e to the x. This function takes all real numbers to numbers between 0 1. You apply this to each component. So you take a linear function composed with sigma. So not much has happened here. But of course, if I compose linear functions, I'm still getting a linear function. But if I compose linear sigma, linear sigma, this is a non-linear function. Okay, not much has happened, but somehow this works brilliantly well. So this is parameterized by entries of A, matrix entries of A and B. Sigma is fixed, nothing else. Now A I took here to be arbitrary, but often you take it to be a convolutional layer. So convolutions you will know in probability or in analysis. So they are simply where things are symmetric. They're given by this form. Yj is sigma ak xj minus k. Okay, so these are special kinds of linear functions. Hopefully most of you would have seen them. If you haven't, you can ignore say special class of linear functions. It's what you get when you sum random variables, for instance, independent random variables. Okay. And the last layer is typically we want a probability distribution. For instance, what move you should make, an expert will make. So you use what is called a soft max. This will take real numbers and transmit them into numbers between 0 and 1, which add up to 1. That's all. Okay. Now, so I've told you the class of functions. How do you optimize? You just use a gradient flow. Just flow down the gradient, except gradient flows have certain problems. They can go to local minima and so on. So there's a bunch of ways in which you avoid these issues. You use variations of gradient flow. Okay. And what is called backward propagation, which is supposed to be a really important thing in machine learning. As people in machine learning also know, this is simply chain rule. So by chain rule, if I take a composition of functions and I want to calculate the gradient, it's the composition of the gradients. So So you take the last gradient and think of that move to the previous layer, etc. Okay, so think of it for a few minutes. It's kind of obvious what is going on, but this works very well. So we simply optimize in this class of functions using various heuristics, but largely this is really what we are doing. Okay, so this was a digression into what is deep learning in case you have not seen this. So back to what happened. AlphaGo was succeeded and defeated by AlphaGo 0, which learned 0 here is the amount of data AlphaGo had, 0 data. It learned purely by playing against itself. It knew nothing but the rules of Go and started off with a completely random policy and values and just kept playing with itself. And this made it much better than Alpha 0. As someone commented, it looked like 2000 years of human knowledge was actually a liability. You throw away all human knowledge, you can get better. Okay, and its successor Alpha 0 uh, no longer was Go specific. In particular, it could play chess. So it was played 3 games: chess, Go, and shogi, as it's called, or shoji. I don't know how it's pronounced. Japanese chess, which is a little more complicated than chess. It took just 4 hours to become the strongest chess player on the planet. That is was already a computer, not a person. And it went on playing with itself for 2 days. It discovered many openings, then discarded some as not going there. It discovered a lot of standard openings, etc. Became far and out these things with zero data. So you might read in the press and so on that machine learning won't work here and there because there is no data. Well, there is no data here. So that is obsolete now. If you know the rules, you don't need that. You can simulate. You can try self-play. Okay, so also more interestingly, it had a dynamic open style and it prioritizes piece activity over material. In particular, it sacrificed queens many times and not exchange. It's really sacrificed it for the sake of momentum and for the sake of position. Now, this is exactly the kind of thing which for humans needs very high level of intuition. Okay, so that what Alpha 0 became good at was really intuitive thinking, what humans would consider intuitive thinking. Okay, it's very uncomputer like. So a bunch of other examples chosen mainly to illustrate concepts before winding up with mathematics again. So one thing is that unlike a chessboard or an image, words are either the same or different, but you want to give them a structure. Okay, so to give such a words a structure in word2vec, which was developed in 2013 in Google research, what you do is you set up the problem of predicting a word given its neighbors, or maybe predicting the neighbors given the words. The latter actually works better. Okay, so you're given, say, the neighbors of the word. You have to predict what word that is, and use that. And the way you predict it is you map words into a space. You embed them into a space. And then you have the next layer where you use some simple method to predict what are the neighbors or what the word is given the neighbors from the first step. Now, it turned out very interestingly that so this had nothing to do with no structure was used, only what words occur. But analogies such as Paris is to France as Madrid is to Spain are captured by vector operations. So if you took the vectors for Paris, France, and Madrid and took the parallelogram with these as 3 vertices, look at the 4th vertex that is very close to Spain. The word closest to that is Spain. So analogies got automatically captured by this. So that is one lesson, that deep structure gets captured automatically by solving problems. The other important lesson here is that if you don't have enough good problems whose solution you need, you create synthetic problems. This is what we do in mathematics anyway. We learn by creating exercises. So you can give your computer system exercises and use that to become smarter, and then use that to solve real problems. Okay, so quickly a couple of other examples. Generative query network is where you have a 3D environment and you're given 2D views from some positions and you're told another position, you have to predict the view. And the way this was done in the GQN was that this 3D image is lies in a huge subspace. If it's 1,000 by 1,000 by 1,000 image, that's a billion points. But you map it into a subspace of just 500 dimension, just 500, and map the solution via this subspace. So this is the way in which you do things. Okay, so this was done in yeah. So then it turns out that if you look at that concise representation, so there is a representation network where things get narrowed, and then from that representation network, we widen again and get, so we don't widen, we map to a 2D image. It turns out that just like word to vec had analogies, you could see that color, shape, and size were discovered. There were emergent properties from these. That is the arrangements of images. So if you took a red ball and a blue sphere and took a blue ball, and the corresponding parallelogram would have a red sphere. Okay. So this is another example. This is an important idea. I'll say this briefly, not directly. One fine evening, somebody walking along thought about this, and it's been quite revolutionary in the field, what are called generative adversarial networks. You take two networks which can compete with each other. A typical example is one which generates, so one is called a generative network and another evaluates these discriminative. Typical example is generating a synthetic image which cannot be told apart from a real world image. And so you make these two compete with each other and they both get really smart. So the common application of this is not a nice one. It's deep fakes, which you will hear about in the news. But the idea is really powerful. I mean, it can be used for many other things. Idea is, again, you train a network, I said earlier, by synthetic problems, but you can also train it by competing with other networks. So all these are clever ideas in which you avoid lots of supervised human training because we don't have the time to train networks that much. Okay, you let networks get smarter by themselves. So this is not relevant, but it's a really nice idea. So in temporal reinforcement learning, just like we had with our value function, what you're trying to do in a chess game is predict how good your position will be several moves in the future. So you play chess to the end, you're trying to predict whether you'll win or lose. So the rewards come in the future, you're trying to predict this. But unlike say chess, sometimes what happens, the example given in this paper was a robot trying to jump over a pit or not, you end up with a bimodal distribution, like in Manjunath's example of that Toeplitz, not Toeplitz, the Hankel process. Okay, that is to say, if you're trying to jump over a pit, you either succeed or you're not. So your reward is either going to be a very positive or it's going to be very big or very small. So the way you get around this, the idea they came up with is you have several predictors. Some are pessimists, some are optimists. So some care more about negative and some about positive errors. And so engineering people came up with this idea. The remarkable thing here is subsequently dopamine cells are the reward centers in the brain. Subsequently, in a collaboration with people from the Harvard Medical School, they found the same mechanism which was invented for machine learning in mice. So it had been invented or in evolution as well, but it was discovered that this invention had taken place in this manner. I mean, first inventing it. Okay, so here quickly there is a so a lot of things used what are called recurrent neural networks, if you have heard of those, but they have certain major shortfalls. Instead, in a paper called Attention is All You Need, an architecture called transformer architecture was invented. And this was where you learn to what words you pay attention. I'll save time by skipping all details. If you have heard of GPT-3 in the news, this is the system that writes poetry, makes essays, all sorts of things that is based on transformer architecture. But much more importantly, this is something you should hear of if you have not heard of it. AlphaFold 2, the second version of AlphaFold, which uses transformers. Details are not yet published, but they say that one of the differences is useful. Solved in a certain sense the protein folding problem. That is, given the protein sequence, how it folds. This is an extremely important problem in biology. I won't solved in the sense that the predictions of AlphaFold 2 were as good as experimental methods. I should just point out that 4 or 5 years ago, protein folding predictions by computers or mathematics were just hopeless. And they were quite poor even just 2 years ago. So they have these regular competitions. And suddenly at this competition, they went from 60% to 90%. 90% is the experimental level. And just a few years ago, it was 20% or so. So this is the things. Okay, so some general comments here. So it looks like we have emergent semantics, that is behavior or understanding, comes by solving problems in these AI systems. Okay, so image processing, the experts say, I'm simply quoting them, that is, I've already mentioned layers, that as you map through layers, you get higher and higher levels of abstraction. Okay. Other lesson that people have learned following word to vec and so on is parts of networks are shared. That is, you solve many problems, but the first few layers are the same for different problems. Okay. In particular, when you went from AlphaGo to AlphaGo 0, in AlphaGo, you had a value network and a policy network, but AlphaGo 0 had a single network. And that helped because the common parts somehow learn the meaning of these. A dramatic illustration of this was what was called zero-shot translation. This came from a very practical problem in Google because the number of languages that Google handles became more and more. They started with hardly 5 European languages and Chinese or something, but they got to about 90 languages. At this point, training for 90 input and 90 output means you have data you need for 90 squared pairs of languages. This became more and more clumsy. You don't get good data on this scale. And even if you got it, the human effort in feeding that data is just too much. So instead, what they did is they changed the design where you gave the input translation, I mean input sentence, and also input what language you want as the output. So you said translate to Japanese and gave it an input sentence and trained with this data simultaneously for all pairs of languages. And then they found that once they had the system, they decided to test, and they gave a pair of languages, Japanese and Korean, which are similar to each other, by the way, but not a single pair in the training was Japanese to Korean, but it still did pretty well on this. And then they tried to investigate further and found it seems to be an internal language. That is, sentences with the same meaning from completely different source languages are mapped to the same place. Okay. So to summarize the capabilities of artificial intelligence, they can make moves we can appreciate. They can judge the value of a theorem, hopefully, but certainly of a bold position based on future rewards. They can show originality. They can acquire knowledge to us which was only tacit, which the older expert systems could not. They can work without data or with limited data or with unstructured data by self-play, by synthetic tasks, or what is called self-supervised learning, which we implicitly do all the time, which a kid does while playing and so on, which is you predict everything in terms of everything else. That is, you see any part of the world, use that to predict the rest of the world. You organize objects efficiently, you capture composition, you seem to discover concepts just by solving problems. Okay, so how about artificial intelligence for mathematical proofs? It has been done. Well, what we can hope is we can iteratively keep doing the following and improve at doing. We accumulate the knowledge, we digest it, meaning find representations and so on. You solve problems and you pose problems and you prove theorems, partly because you want to solve those, they're important questions, partly just to accumulate knowledge. We know that this we know, we don't know this, we make a conjecture and solve it, or simply as exercises to digest knowledge. And along the way, we develop judgments, whether a statement is true or not, how important it is, how difficult it is. We all do this as human mathematics, and this is a nice positive feedback loop. Okay, all this looks very nice. The problem is, of course, you might stagnate or be confined to some types or some areas. You want to avoid this. That is really the challenge. How can you build such a system and which doesn't get bounded or localized? Okay, you need to do many things. In a game, you're given already what an outcome is. In a theorem, in mathematics, you know what a proof is of a theorem and what isn't, but you don't know what is a silly result and what is a non-trivial result. You have to find good ways to formulate it. You have to find good composite moves because you don't want to go down to simple moves. You want to integrate with experiment, with solvers of the kind I mentioned, with the literature. Also, you not to be strategic. When do you give up? As a human, I've never learned this, and we all struggle with this. Okay, so machine learning has been used in automated and interactive theorem proving by various people. I won't name them because I'll forget some. I mean, I'm not an expert in this. For example, for premise selection. So you're given a problem, you have to know what existing theorems to use for it. Also choosing tactics and parameters. I have myself been working along this. along the lines that I've sketched here. So I obviously use all I know, and I tell you all I know. So there isn't more to add on that. And it's crucial to be able to learn from existing mathematics. Okay, of course, Alpha Zero learned from nothing but the rules. So we could learn from nothing but the foundations. But I do believe mathematics is enormously more complex than chess. And so trying to do an Alpha Zero act is too hard. So there are two ways you can learn from existing library. You can use a formalized library like the Lean Math library, or you could use some natural language processing to read a paper, human papers written for humans. Okay, but how about the converse? So we want computers to learn from us, but we want to learn from computers as well. If computers become good at proving, we don't want a situation where they keep telling us these are true and maybe spit out proofs that they can check, but we don't understand. So value of a mathematical proof is not only to tell you what it's true, but we learn various things from it, in particular how to prove more from it. Okay, sorry. Okay, so here is an example of an incident which I will say in 2 minutes, because I'm sorry I'm in a minute over time, but I'll quickly say. So Terry Tao's blog had a question which Apurva Khare, a colleague, asked in him. And this was answered in 6 days in Polymath 14, what became Polymath 14. A crucial step was a computer generated but human readable proof I posted. Okay, so this is the proof extracted, and indeed, this is how it was first posted. It's still on the web. It was posted on the web. And what this proof was studied by Pace Nielsen, who remarkably said between line this and this, the computer did so, between line this and this, you did so. Then he discovered something called the internal repetition trick, which he said the computer is using. And Tobias Fritz understood what he did. So after Pace Nielsen extended using the computer's method, he extended it further. And then Terry Tao started asking them things. All this was happening on a blog. Once he realized something was up, and then he abstracted this, and Fritz took a different special case of the abstract lemma. And this gave the key lemma, which actually not only answered Apurva Khare's result, but gave a very nice structure theorem. Okay, so this was published as Polymath 14 with 6 authors. 5 of the 6 I've mentioned. Leo Silberman is the 6th. Okay, so myself, Nielsen, Toby, Fritz, Tao, and Apurva are 5 of the 6. Silberman was the 4th. Of course, there were other dimensions to this. I've only mentioned a short thing. When I subsequently wrote an account of this, there were a couple of issues raised. One very important one is, what about the replicability? So this was generated in an interactive session. I had written programs, but I was running them in a console. Okay. And so what was this a freak? Can you discover, well, not literally that proof, but a similar proof? Okay. And another question was raised. And so to illustrate that, I recalled what I did roughly and wrote a script running the same program, which is here. Okay, this is a script running on my laptop, no supercomputer, no data center, which generates a proof which is a little different from the previous one, but not that different. First thing is, it took 173 lines. The other one was 127, so it was a little more efficient. But the bound is a little better here to compensate for it. It is a proof of a similar nature to be generated. As you notice, it took 2 or 3 seconds to generate. If you wish, I can run it with a time. I'll run it with time in a moment to generate these things. So my point here is that in a replicable, so this is robust. It's also nice to see something actually happening rather than just talking in the abstract. Okay, so yes, it wasn't a freak that it happened. It can be just using some very rough principles and the same algorithms. You can generate another proof of a very similar nature. It runs fast. It doesn't take massive amounts of computing time. A good laptop can run it in, I'll tell you how many seconds. The other issue raised was, what about rounding of errors? Well, that can be solved by using rational coefficients instead of real. Okay, this problem, everything was rational, and indeed here is at the end of it a rational bound. Okay, in fact, at Apurva's suggestion, I had switched to rational numbers, but that's much lower than real numbers. So the proof is first generated using real numbers and then mapped to a rational proof. Okay, so let me see, just for fun, let's see how long this took. Okay, so the moral here is that yes, humans can learn from computer proofs. So far as I know, okay, it took 4 seconds of time to discover this proof on my laptop, 4.7, almost 5 seconds. But the moral here is that hopefully people can also learn from computer generated proofs. This is, as far as I know, the only so far the only instance in the literature. But if computer proofs are appropriate, it won't be a one-way street. Not only can computers learn from us, we can learn from them, and hopefully have new ways of doing mathematics. Okay, so with that, let me return to my slides, and thank you. Sorry, I'm a couple of 5 minutes over time. I'll be happy to answer questions if there are any. Thank you.
So, are there any questions in the audience? Yes, there is one.
I have two questions. You briefly talked about back propagation. I
Yes.
legalities of it. I mean, I was eavesdropping on a couple of friends talking about it.
Yeah.
So when you back propagate, there's something like an error function which you have to minimize and
Yeah.
assume any problem which you can fall into a local minimum. So
Yes.
for that, the in the neural network, it keeps adding some cost function so that you don't get stuck in the local minimum. And if it goes to a global minimum, the cost function is such that it settles there. So,
Yeah.
yeah, intuitively speaking. But what if something like that never happens? What if
Huh.
there so what I'm leading up to is, say AlphaGo is playing some chess player, and then there is a position in which either the queen sacrifices the move, or there is some other move, and both the lines are equally beneficial for both the players. Now, will AlphaGo sacrifice the queen, or will it wait, or will it do as any human being would do and not sacrifice?
Right. So there are many dimensions to this. First of all, none of these actually find a global minimum. Okay. They try their best to find a global minimum. Okay. So if even if you had a global minimum and another one which was very close to minimum, not even exactly equal, you could very well go to the wrong one. Okay. These are all, that's one dimension. Let me emphasize though, by your usual Gödel Turing results, you in fact cannot be guaranteed to find the global minimum. You see, you would be able to solve, for example, the word problem in group if you could find the global minimum. So there is no algorithmic way to find the global minimum. So the thing about heuristic methods like and machine learning is very heavily heuristic, is that there are situations where it is simply not going to work. We know that for conceptual reasons. Okay, so there's lots and lots of ways to avoid it. uh, all you can try to see is empirically, does it work often in practice? Okay, it's not going to always work. It's never going to be. So you wanted to do it, you also have resource and time limitations, and you try to find the best answer you can, and for many problems in practice it finds a very good answer. That's all we know. And that's not all we know. What we know is it is not going to find the best answer for all problems. And not just it, no algorithm can. Yeah.
Okay.
Yeah.
So the other thing is, as you said, all pieces have points.
Yeah.
So there is this player Bobby Fischer. He considered bishop to be 3.5 and knight to be 3.
Right.
Kasparov also probably agreed. So does AlphaGo also have its own ranking and its own
No, that is the point here. Okay. No, it's a good question. You see there. So this is really where I want to maybe emphasize the point. Okay. So I then, with limited times, let me just go to the chess slide here. Okay. So I'm just keeping this chess side on because there's nothing in the slide which will answer your question. Okay. So you have chess and Go, and you have the contrast here. Okay. So deep blue is what is called an expert system. So the first wave of artificial intelligence, which started in the 1950s, went on through 1960s and 70s. And then you hit what was called the AI winter, artificial intelligence winter, when there was no progress for many decades. The reason this happened is during the 50s and 60s, up to around 73, 74, people had great hope for artificial intelligence. So the AI researchers got the best computers in the world. By around 70s, they realized this is failing. It solves some problems, it doesn't solve other problems. And so AI researchers stopped getting things. So there was not that much progress. But IBM, for its publicity reasons, it's a computer hardware company, to show that its computers are very powerful, spent a lot of money on hardware and on training what is called an expert system. An expert system is where human experts try to codify their knowledge. And the first wave of AI people like Marvin Minsky and so on, were very focused on how do you represent knowledge, how do you capture it very well, etc. Okay, so that was the thing. So what you're talking about is pieces. It's not just the value of a piece, value of the relative position, everything else. You try to capture in more and more elaborate rules how many points you tweak, how many points per piece you give it positions. So for example, already when you're talking about a bishop or the value of a bishop, if a bishop of white is mostly attacking other white pieces, I mean moves towards white pieces, its value is less. So there are positional values, etc., etc. And this approach hits a ceiling. It's enough to be a champion chess player, but not even a champion Go player. Not managed to translate things, not managed to recognize images, not managed to do mathematics, etc. Now in 2008 or so, you had a major transition. And the reason for this transition was not really new ideas. The ideas were came up due to people like Hinton in the 1980s. Jeff Hinton, Jan LeCun, and Joshua Bengio. These are the three leaders, all were then based in Canada. So they developed the idea, starting with Hinton, of deep learning already in the 80s. But the point is that learning actually takes a lot more computing than just carrying out rules. So what happened between 80s and late 2000s is the underlying hardware and compilers and so on got much better. So then it became feasible to follow the deep learning approach. Now with deep learning, you do not have something. So when you have a chessboard, the chessboard is a bunch of numbers which tells you what is in what position. And you have an extremely complicated function which will tell you how strong white is and how strong black is. And that function is, as I said, a composition like this of many, many layers. Okay. These things grow very fast with time, because a few years ago, I remember listening to a talk of Ingrid Dauberschies where she was talking about how the limitation technically now is 9 layers, though she has heard some systems have pushed it to 11 layers. GPT-3 has 96 layers. So these things go explosively deeper. But what I'm saying is a composition of even 10 such functions is something which, and each of these functions depend on a very large number of parameters. So we cannot describe it in these human senses. It is not simply the position of a piece and this and that. It is how we think intuitively. We don't know why this is strong, why this is weak. So essentially, it's the chess player's intuition which goes beyond. There are many very interesting experiments here. Okay, so in terms of this, I'm simply mentioning this because it may be interesting. So one of the things they found is, which shows how chess players understand things. A grandmaster could remember they tried with board positions, ordinary chess player versus a grandmaster, and the grandmaster could remember the chess positions way better than the ordinary player. Then they decided they should really check this experiment. This is only true provided it was an actual chess position from a game played by expert players. That is because the grandmaster represented the game in not as a set of pieces, but at some abstracted level, the way these things are. So when they changed from actual games to random chess pieces, they suddenly found grandmasters are no better than ordinary people. It's not that grandmasters have a better memory, they have a semantic representation. So similarly, the deep neural networks are picking up semantic representation.
No, my thing was different. I mean, as you said, it's true that if it depends on your position, that's true. Saying if you start with the opening position, is do the computers need to be fed with which pieces are more valuable, or does it?
No. So as I said, Alpha 0 started with zero data. Alpha 0 knew nothing but what is a legal move and what is an illegal move.
Okay.
Nothing but that. So it rediscovered standard openings. So it knew where a pawn can move or where a knight can move, but it was fed with no even so deep blue was fed with lots and lots of things, opening tables, endgame tables, experts knowledge of moves, etc. When it came to AlphaGo, the original AlphaGo was fed with data of how people played, but again no rules saying this. So in chess you could think that an equivalent of AlphaGo would simply see lots and lots of experts games. However, Alpha Zero, which is what was shifted to chess, there was no AlphaGo equivalent in chess, simply knew nothing but the rules of chess. So it started off as a horrible player because it would move things completely at random. But it kept playing with itself. By the way, 4 hours is a bit misleading because there were 5,000 processors in parallel for those 4 hours. But still, I mean, this basically DeepMind was acquired by Google, and large part of the motivation, as Demis Hassabis, who's the brain behind DeepMind himself said, large part of his motivation for getting acquired with Google is happy to sponsor lots of computing time for them to train their machines. Yeah, so there was heavy training, but nothing but the rules of chess. And what I'm saying is, it's not that it discovered points, it discovered something more complex and abstracted, as we do also in other tasks. Yeah.
Do we know what it learns, or is it completely a black box?
Huh?
Can we know what it learned, or is it like a black box?
Right. So it is not a black box, and you do poke around things and you can try various things because all its coefficients are known. So you have this bunch of functions, okay? And these functions in turn have dependent on matrices. And you know all the matrices,
Hmm.
okay? So what do we mean by knowing what it learns? So at this point, it becomes like studying a biological system.
Yeah.
Okay. It's like studying our own brain, or you study the behavior of a horse, but you have complete data. Unlike a biological system where experimentation is expensive, it's like studying the brain, except that with the brain, it needs enormous skill. And now they do have optogenetics and this and that to make measurements. But here, you know what every neuron is doing at every time. But that doesn't mean we understand how the brain functions. So because of this, we can understand all sorts of things. So these are examples I gave here are, for example, in image processing people, when they ran through an image recognition, you had several layers. So you could see what happened when you went to the first layer. And I'm quoting, I'm not an expert to say, so I should disclaim that I'm only simply quoting what the experts say. But they say first layer captures angles, lines, and so on. The next layer captures the next level of features of objects. So as you go through each layer, you capture higher and higher levels of abstractions of the relevant object. And so similarly, when I talk about interlingua, you can actually look in a neural network and see what the coefficients are. However, these are an enormous number of coefficients. So you have to ask a question and probe, and you may be able to answer and you may understand something. Yeah. But that's what it's like studying a cell or something like that. I mean, yeah.
I can just go back to the first question because I just have one more thing. So as you said, it's not always. I mean, it's almost always not the case that the global
Yeah.
minimum. So it feels as if this is something closely representing a human being because even in our case, if we play chess, then there are two moves, both are equally likely. We just take a chance.
Yes, that's right.
There seems to be something in the algorithm that does not make the computer keep searching for more and more and just, take a chance and see what
You
happens.
just do what you want. And I'm saying chess may be not such a good analogy because we are not naturally hardwired to play chess. Think of swimming or cycling, which is something which is a much more human activity. When you're cycling, you're balancing on your cycle through adjusting your body weight, your handlebar, etc. Of course, helped by gyroscopic effect, etc. But if you set a robot with rules on a cycle, machine learning robots are able to cycle these days. But in fact, a typical example of machine learning, Andrew Ng, who's a leader in this field, pointed out one of the hardest problems in control is flying a helicopter, which is actually very difficult for a human because it's unstable like a bicycle. Okay, but they're pulling joysticks and so on. They are not finding an optimal way. They are keeping it stable. There is more than one solution. You find a solution, but you find a good enough solution. You find the best you can, And if the problem is easy enough, you can find such a solution. You're skilled enough. And if the problem is too hard, then you just don't find such a solution. Similarly, when you're doing mathematics, you try something else, and it's not that you're trying the best thing. Some people are better at what to try, some people are not so good at what to try. So we cannot really find optimization for hard tasks. What we want to find is a good solution rather than an optimal one.
But I use the example of chess because it's a closed game. The machine knows that at some
Yeah, right. True, fair enough. It's a good example.
there's more incentive for the machine to just keep decisions like
Yeah.
his.
Yeah, no, it is, chess is a very good example. But I'm saying the difference is that expert systems are also very good at chess. Okay, so if you write down rules, expert systems are very good at chess. But there are lots of things, including mathematics, at which expert systems are actually hopeless. And that is where where the difference between intuition, learning, and a codified rule stands out the most. Things at which really expert systems are hopeless and humans are pretty good. Okay, like flying a helicopter or swimming or cycling or doing mathematics. Yeah.
So, are there any more questions here? So, we'll just go to the YouTube section. Haseen, are there any questions in the YouTube?
Pranav, there are no questions in the YouTube channel.
Right. In that case, let's. Yeah. So there is one more question here in the audience. Yeah, Aman.
Sir, you said you have got a solution in 5 seconds. Uh, some problems are like open problems in mathematics. So that can be solved by artificial intelligence.
No, that's a very good point. No, I got a solution to one very specific problem. And that was because there was an algorithmic one. By the way, the 5 seconds is the running time. I did not solve it in 5 seconds. Okay. Post facto running time, the actual computing time was 5 seconds. Okay. And this was not an AI system, by the way. It was completely algorithmic. And it happened that that particular problem was suited for algorithmic solutions. There are people working, including me, on AI attempts at mathematical systems. So far, with the exception of the Robbins conjecture, and that was the older wave of AI, there have not been too many solutions. Okay, so this one I did, one because it's nice to see something running instead of just having general talk. Second, the lesson is that you can have computer generated proofs which we can read and learn from. Okay, that is the thing reason that was the moral I was trying to show. And I was trying to show that these days computing power has become quite a lot. That's something which is way beyond human capability. Okay, so even though this was algorithmic, people, including the smartest mathematicians in the world like Terence Tao, could not unassisted find things that a computer could find. And then it needed humans to do pattern matching in this particular case. In the few seconds, yes. So when will AI start solving open problems in mathematics? That's what I said is not is the question. Is it in 1 or 2 years? No chance. In a decade or so, 2 decades? I would think yes, but that is really the question. In a century or two, I think it's a virtual certainty. Okay, that AI will solve. And all my examples were trying to illustrate that why I would justify this answer and how one could try to do this.
So, any more questions here in the audience? So, I guess not. So, let's thank Professor Gadgil for the excellent talk.
Okay, thank you.
And I'll request you to drop down to